Hello, good morning to all of you. Towards the end of the last lecture, I had started talking about what are known as Kirchhoff's laws. Basically, before we did that, what we realized is there are several combinations of resistances which can be reduced to series or parallel combination, just the way we did it for the capacitors. But of course, there is a slight difference that we pointed out, that the formulae for the series resistances go the way the formula for the parallel capacitances go, and vice versa. However, it is very unusual to have situations where circuits are simple enough to be reduced into equivalent parallel or series combinations. And in general, we have a set of two laws known as the Kirchhoff's law, which can be used to find out the currents in such complicated circuits. So there are basically a set of two laws. The first, what we did is to define what is meant by a junction. So what we said is, a junction is a point where three or more conductors meet. So there is a rule regarding the junction law. So first law, as we talked about last time, is called a junction rule. So junction rule simply says that if you assign a sign to the current which is coming in, you can do it anyway. Supposing the current which is coming in is taken to be positive and the current which is leaving that junction is taken as negative, then the algebraic sum of currents at a junction, so which is what I write like this, sum over I is equal to 0. This is algebraic sum of current at a junction. Let me also state the second law, and then we will do a slight discussion of both. And this is what is known as the voltage law. So this you might call it a current law. So voltage rule. So voltage rule basically says that the algebraic sum of voltage difference around any closed loop. So sum over I Vi equal to 0 around any closed loop. So these are basically the two things which we are concerned with, and I will in this lecture discuss the applications of these laws by giving you several examples. So let me first talk about junction rule. So basically, the origin of junction rule lies in the fact that electric charges do not accumulate. There is a continuity of electric charges. So whatever is coming into a junction have to go out, and that's what we meant by saying that the algebraic sum of currents, because as you know, current is nothing but rate of change of charge, and so therefore the charge cannot accumulate at a junction. That's the simple reason why a junction rule is valid. So let me illustrate this. I am not giving any circuit, but let me say that I have a junction of this type. Let me just draw some points here, then I will. So what I have done is this, supposing this is I1, let me say this is 4 amperes, this is 3 amperes, this is minus 2 amperes, so something like this, 4 amperes, Let's call this I2, which I don't know. This is 2 amperes. This is I3, let us say, and this is 2 amperes. So look at what I have done. I have several junctions in this circuit. So here is a junction, this is a junction, this is a junction, this is a junction. Any point which has 3 or more resistances or conductors going out, that is what it is. So let us look at how I can use junction rule for this. So I will assume that a current which is coming in is positive. Let us say there is nothing special about this assumption. If you wanted, you could have assumed that the current which is going out of a junction is positive, in which case that current that is coming into a junction will be negative. So let us look at this first junction. So I have I1 coming in, so that is positive. I have 4 amperes coming in again, so that is positive, and there are 2 of them going out. So I put a minus sign there. I have got minus 3 and you have minus 2, because there is a 3 ampere going out here, 2 ampere going out there. So if you look at this, so this quantity is equal to 0. Okay, I have written I1 here with a minus 2. What it actually means is that the current in this branch is actually going in, but that's easily remedied by writing this as minus of minus 2. So let me take it as plus 2. So let me make a note here that this is shown as going out, but a negative current going out. Why am I doing this? See, very often in a circuit, you have no previous knowledge of the direction in which the current is going. So you assume some direction, and if the result turns out to be negative, then you know your original assumption was wrong and the current actually flows in the direction opposite to what you have assumed. So there is no problem. I have minus 2 going out, which also means plus 2, the direction is actually opposite. So that is what I have taken care of by writing this as minus of minus 2. So look at this, this tells me that I1 is equal to, this is 4 plus 2 is 6, so it is minus 3 amperes. So what am I trying to say here? What we are saying is that what you have done is probably wrong. It's not wrong, but I1 is turning out to be negative. In other words, my actual direction of current here should have been like this. So you look at how this actually works. This is minus 3, which means 3 amperes going out. This branch has a 3 amperes going out. This branch has a 4 amperes coming in. This branch has a minus 2 going out, means plus 2 coming in. So 6 going out and 6 coming in, which is what we expect. And like this, you can also, for instance, look at what is happening to this second branch, a second junction. So let's talk about junction B, let's say. So this was junction A. Now what happens in junction B is this, that in junction B, I have said I2 coming in, so I have got I2 is positive. There is a 1 ampere coming in, there is a 3 amperes coming in, and there is a 2 amperes going out. That's equal to 0. So I2 plus 2 is equal to 0. So I2 is equal to minus 2 amperes. So once again, the minus sign simply indicates that the direction, as we have assumed in our example, should have been actually opposite, but that doesn't matter because I have got the right sign there. So let me look at now the voltage rule. Actually, junction rule is very easy to implement. It is a voltage rule which you have to be a little careful, nothing so special, but you have to be a little careful. Basically, the origin of voltage rule comes from the fact that in a static field, my integral for a static field, this we have repeatedly talked about, that closed integral of E dot dl is equal to 0. So the net EMF, if you recall, integral E dot dl was defined as my EMF. So the net EMF in a closed loop must be equal to 0. Now in doing so, I need some working method, and this working method is the following, that once again these are simple convention by which you could do your problem. You could decide that you want the opposite convention, nothing would go wrong. So let me look at this. Supposing I have a current which is flowing through a resistance, and let's suppose this resistance is R, and suppose the current is entering in here. Now the end of the resistance where the current enters in, remember current is the direction in which the positive charges move. So therefore, this is at a higher potential. And at this point where the current is actually moving out, that's at a lower potential. So therefore, if you are moving in the direction of current, then the potential actually drops as you move. So moving in the direction of current, change in the voltage is it drops, so delta V is negative. And how much is this? This is simply equal to IR. So drop is IR. So this is a drop. Now since it's a drop, when you write down in an equation, you would put a minus sign in front of it. That is, we'll work this out. Now there is another thing. The circuit, in addition to resistances, also has seats of EMF, the battery or things like that. Now again there, we know that when a positive charge moves from negative terminal to the positive terminal, it gains energy. So therefore, across a battery, delta V is positive, namely the potential rises in going from a negative terminal to positive terminal. So these are the 2 points you need to remember. Once again, it doesn't matter whether you know the polarity or not. Now, if you know the polarity, then of course you know, you have an a priori idea of which direction the current is flowing, and these will be easy to use. But it is possible you don't know the polarity, in which case assume any of the ends to be positive, proceed using the same thing. You will turn up with a negative sign at the end of your calculation, in which case it will help you in fixing up what you actually want to do. So let me again, without going to a specific circuit, give you an example of how it works. So let me just draw. I am not putting in any items here. All that I am doing is this, I am putting some blocks. It simply says it could be anything. It could be a resistance, it could be a seat of EMF and things like that. Alright. So what I do is this. So let me just draw these. So I will put some a priori signs there. Supposing I have this as minus, this as plus, and this is 8 volts. This is plus, this is minus. Let's call it some V1, let us say. This is plus, this is minus. This is 8 volts. This is plus, this is minus, this is again 8 volts. The numbers I have taken to simplify my calculation. And then now I have not indicated what these are. Now, how does one find out what is V1? And that will also tell you why I did not put anything here. So the way it works is this, that I have to identify a loop and go around that loop. And the net voltage difference, once I come back to the point where I started, that will be 0. So let me say that I start here. So when I cross there from this point to that point, my voltage rises by 8 volts. So I have written plus 8. Here, this end is plus, this end is minus. So therefore, it drops minus V1. See, what I am doing is this. I am not going to go around this. That is because this data is not known to me. But what I will do is this. This loop law is valid for any closed circuit. So notice this. Supposing I start at this point is A, B, C and D. Now this is a closed loop. I just go around in that. So if I do that, I got next one again from plus to minus. So therefore this is minus 8. Once again from plus to minus, another minus 8. Then I come like this, minus to plus, so therefore it is plus 6. Here again plus 10. No details of the circuit I have written down. If it's a battery, then the positive, the rise in the potential is when I go from its negative terminal to the positive terminal. If the element there happens to be a resistance, then in the direction in which I am going, in this case I had decided to go like this. That is the assumed direction of the current. Then there is a potential drop as I go through a resistance. But here I haven't necessarily assumed what type of things are that. Whether it's a resistance or it's a battery, I have had a way of handling it. So look at what this tells me. This simply tells me V1 is equal to, well, you add them up. So this is 16 minus 8, so that's equal to 8 volts. So let us start with a simple problem. Supposing this is 12 volts, this is plus, this is minus, this is 4 volts, this is plus, this is minus. This is a 1 ohm resistance, this is a 3 ohm resistance. Now what do I do? See, the thing is this circuit doesn't have any junction rule. It's the simplest circuit you can think of. And so therefore, you assume there is no junction, so only voltage rule is there. You can decide which way to go. There is a positive here, there is a positive there. You could have decided to go like this or like that. But it is totally immaterial how I want to go actually. So let us suppose I go like this. And the reason is very simple, because this is the positive end of the battery, of a bigger battery than this. So therefore, presumably the current will go like this. And let the current be I. Then you notice what's happening. I have started from here. So when I go on the resistance-less wire, there is no drop of potential, but there is a drop here. Because I have assumed the current to be in this direction, so there is a drop of I into 1. So therefore, I will write this as minus I into 1. Once again there is a drop here, so minus I into 3. This is going from positive terminal to the negative terminal. One more drop, so therefore minus 4. And here I go from negative terminal to the positive terminal before I come back to this point, so therefore there is a plus 12 there. And that must be good. So this tells me that I into 4I is equal to 8. So current I is equal to 2 amperes. This is a situation where I have a single branch. And let me increase the branches a little bit. Say 2 ohm, this is 12 volts, this is 6 volts, then this is, let's take this as, since I'm just illustrating something, let's take this simple. Okay, look at this situation here. I have 2 batteries, I have 3 resistances. Once again you realize there is no way of reducing this circuit to a parallel or a series combination circuit. So what do I do? Now I have 2 loops here. Now let me say I want to go like this. But before I do that, let me first use, say there is a junction here. There is also a junction here. There are 2 junctions. But these 2 junctions I will write down by assuming some, so this is first junction. So let me assume this current that is coming out is I1. Coming into that junction is I1. And let's suppose that this is going like this to I2, and let me call this I3. But I notice this I3 must be equal to I1 minus I2. Because I1 coming in, I2 going out, so I've got net coming in is I1 minus I2, so net going out through this must be I1 minus I2. Okay. Having done that, I have got 2 unknowns, which are I1 and I2 are my 2 unknowns. So I1 and I2 are 2 unknowns, and I3 is known already because it is nothing but I1 minus I2. So therefore, let us look at the left loop. So what I get is this, that since coming in is I1, the amount of current that is going out from here is I1, what is coming inside must be also equal to I1. So let's do that. I've got minus 2 into I1 minus I2, supposing I started from here. Then I got minus 2 I1, this is this one, then plus 12, that's equal to 0. That's one equation. The second equation, you do it from this loop. Now once again, it doesn't matter how you assumed it. So let's suppose we go like this. So if I do like that, I have a minus 6 there, minus 2 times I2, but this time since this loop has been taken like this, it will climb up. So therefore, it will be plus 2 times I1 minus I2 equal to 0. So I have got 2 equations in 2 unknowns. I will not be unnecessarily solving it here. The idea is to tell you how to solve this equation. It's a trivial simultaneous equation and you can yourself solve it. So 2 equations, 2 unknown, so 2 equations. Now notice the second equation. I need not have done it on this loop. I could have also done it in the bigger outside loop. And it will be an independent equation. Let me take some more. We have given 2 loops now, let me give you 3 loops. So let me give you some numbers. Let it be 6 ohms, let it also be 6 ohms, 3 ohms here, and 3 ohms there, 6 volts there in this way, and a 12 volts there that way. So once again, what do? I can assume directions, but look at the following first. That this section of the circuit is a parallel combination of 2 6 ohm resistances. So therefore, the effect of these two is equivalent to a 3 ohm resistance. So therefore, this circuit that I have written down, I could have first simplified it. Now I will first solve this equation. So let's look at that. Supposing I assume that my current that is coming in from here is I1. There is a 3 ohm here. And let us suppose an I2 is going out from here. Now this junction, suppose I have a current I double prime which is going through. Now remember, I double prime is not really current in any one of these two. It is a current through an equivalent resistance which I have found out. So what I will do here is this, that I have one equation which is I1 junction rule. I1 is equal to I2 plus I double prime. This is the first junction. Now then I have the following. Now notice that once I have done that, I don't need any more junction rule. The reason is I have 2 loops, I have 3 unknowns here, I1, I double prime and I2, one is taken care of by the junction rule, and the second one and the third one will be taken care of by choosing two loops. So look at this now. So this was a 12 volt. So minus 3 I1 going like this, minus 3 I double prime plus 12 is equal to 0. So in other words, I1 plus I double prime is equal to 4. This is one of the equations. In the second loop, what I've got is, so this was my right hand loop. Let me look at the second loop. In that loop, what I've got is 3I2. So remember that whatever is coming in. So I write down 3I2 minus 3I double prime equal to 6. Okay, what I have done actually is this. Actually, I should have written minus 3I2, this is I2. Then I am going up the current, so therefore plus 3I double prime, and here I get a plus 6, but this is the same equation as that. So using these, you will be able to solve for the things like what is I double prime and what is I1, these are the three things, and I've got the equations corresponding to that. Now having done that, what you will find will be the following, that your solutions will turn out to be, I am not solving this because they are trivial equations, and so this is equation number 1, this is equation number 2, this is equation number 3. What you get is I1 equal to 10 by 3 amperes, I2 equal to 8 by 3 amperes, and I double prime equal to 2 by 3 amperes. But you recall that I told you I double prime is not a current through any of the branch of my original circuit. But I can see what happened there, because this I double prime came from this circuit, and these are two equal resistances. So therefore, whatever is coming in there must have been equally distributed. So therefore, if you call this, let us say I3 and that as I4, that must have arisen due to the I double prime. So therefore, I can assume that I3 equal to I4 equal to 1/3, half of I double prime, which is equal to 1/3 amperes. I would advise you, instead of doing this part, to start doing directly by assuming I1, I2, I3, whatever the way we have written it. And you have got two junctions there, and you have got 3 loops there. You can do it another way instead of doing this shortcut. Couple of lectures back, we talked about an infinite resistance circuit. Let me give you an example of how it works in this situation. At that time, we had simply asked for, using the concept of parallel and series combination, we were asked to calculate what is the effective resistance. What I will do is do the same thing, but I will now put a battery in one end of the circuit. So let me draw this circuit. There is a 6 volt battery here. This is not quite the same circuit as we did earlier. Let's say this is 1 ohm, 1 ohm, 1 ohm. This is 2 ohms, 2 ohms, 2 ohms, and this continues in an infinite ladder. Now the question is this: what is the current that passes through this resistance? So let me say that how much is this current? Now let's look at that. So we will assume the following. We say that suppose I assume my resistance R, okay, to be the equivalent resistance there. Then this circuit that I have got, I can do like this. See, imagine, forget about this battery. Look at how this works. I have a resistance here and a resistance here. Now supposing I were to cut it here, then what remains is exactly similar, because I have said this is infinite. Actually I should use the word semi-infinite, because on one end I have kept it, but it is infinite that way. So if the resistance of this whole thing is R, then what I am getting is the following. I am getting a circuit of this type. There is 1 ohm, I have got it 2 ohms there, and I have got a resistance R there. So this, now this 2 ohm and this R, they are in parallel. So therefore this is equivalent to a battery, 6 volts there, a 1 ohm here, and an effective resistance there. So this is 1 ohm, and this is the combination of 2 and R. So this effective resistance is 2R divided by 2 plus R. Now notice what I am saying. Now this tells me that the current through this circuit will be the series resistance of 1 ohm and 2R by 2 plus R. But then if I did not cut it here, I consider the whole situation, that is nothing but a resistance R. So therefore my R should be equal to 1 plus 2R by 2 plus R. Solve this is a quadratic, very simple. So R will turn out to be equal to 2 ohms. R will turn out to be equal to 2 ohms. Just take the quadratic equation and take the positive solution there. So therefore, what is the current through the circuit? The current through the circuit is what you do here. So current is 6 divided by, this is just a series resistance. So 1 plus 2R divided by 2 plus R. 2R is 4, 2 plus R is also 4. So this is equal to 6 divided by 1 plus 4 by 4. So that's equal to 3 amperes. So therefore, what we are saying is this: this 3 amperes that we have got is passing through my 1 ohm resistance, because that's the one which came there, and it distributes to this 2 and R, which is also 2, because this was R. So this current that is going in there will distribute here as well as to this part. And since this resistance is the same as that resistance, the current through the 2 ohm resistance is, that the nearest 2 ohm resistance is 1.5 let me write down nearest 2 ohm resistors. Let us make things a little more interesting. This time, since we have already learnt about a capacitor in a circuit, the way I would do it this, let me draw a circuit this time with a capacitor. Okay, so this is the thing. So what we want to know is how much is the current which is passing through, let us say this one. Let us give some names. The first thing that you should understand regarding direct currents that is passing through a capacitor part. Now remember, once equilibrium is reached, there is a direct current. So no current can pass through a capacitor. The capacitor plates of course get charged, but so there would be a potential difference across them, but current is not passing. So what it tells me is this, that there is no current which is flowing through this resistance. So no current here. That doesn't however mean that there is no current through this one. And the reason is very simple, that if current came through this, it will get stuck here. So therefore there is no path. But current can be there in this because there is another loop of which it is a part. So first let us write down no current through capacitor. After transients have died out, there are no current in a DC capacitor situation. Okay, let us now start giving some names. Supposing this I call it as I. Then let us call this I3. So you notice here at this junction, I have I3 going out, I have I coming in. So therefore, at this junction, what is coming in is I3 minus I. So clearly I3 minus I comes here. Since there is no current in this branch, so what I have here is also I3 minus I. So effectively, so far as current is concerned, I have taken out this part of my circuit. There will be potential difference, but this doesn't contribute to my voltage law. So let's look at this here. The simplest thing to do in such situation is to make some intelligent observations. And the first observation that I make is this, that between these 2 points, let's just number them, let's call them AB. So between AB, I know the potential difference because this is not contributing to my circuit. So the potential difference between AB is the same as the potential difference, let's say, across A prime, B prime. but which is 6 volts. So therefore, so let us write down potential difference across AB is equal to potential difference across A prime B prime, which is equal to 6 volts. So therefore, my current I3 is simply 6 by 4 ohms. So therefore, it is equal to 1.5 ampere. So one unknown thing has been removed. Now what I do is this. I look at this loop. In this loop, let's do my Kirchhoff's law. So I have got minus I3 into 4. Remember, I3 is already known. This current here is I3 minus I1. So therefore, minus I3 minus I1 into 2 plus 2, because I am going like this. Then there is a plus 3 here, minus I3 minus I1, I3 minus I into 3. Well, I3 minus I. So you will be able to now remember that I already know what is I3. So do that. This is a trivial number. So you get I equal to 1.7 amperes. That was the only unknown that we had. Now, supposing I am interested in finding out what is the potential drop across these two. So let me redraw that circuit, and what we have shown is that the current I was equal to 1.7 amperes, I3 is 1.5 amperes. So therefore, the current in this section A to C, which was I3 minus I, is actually minus 0.2. So I have shown it as the direction opposite to what I took. So in this section, I minus I3 amount of current, namely 0.2 ampere current is passing. Now my question is, what is the potential difference across the two ends of the capacitor? So let's call it D. So what is the potential difference across CD? Now this is fairly simple. Remember that in this section there is no current. So therefore, the potential drop across these two plates is the same as the potential drop across C and A. So this is equal to delta VCD is the same as delta VCA. And I know the current here. So therefore, by the rule that we have been repeatedly talking about, when I go from C, so let's talk about VC, then I go down the potential hill. So therefore, minus, this was 2 volts, further minus, current is 0.2, so 0.2 into 2 ohms. And with that I come to this end, and since there is no current passing through this section and this is the resistanceless wire, so therefore I can come to point D. So this is equal to VD, which tells me that VC minus VD is equal to 2.4 volts, and that is the potential drop across the plates of the capacitor. And since Vc is at a higher potential than Vd, this side of the plate is positively charged and this side of the plate is negatively charged. In many problems, blind application of Kirchhoff's law is very time consuming and becomes clumsy. However, often symmetry of a problem helps us in reducing the difficulties associated with application of Kirchhoff's law. To illustrate this, let me consider a cubical network of 12 conductors. So let me draw this. I will not be showing the resistances with wiggly lines, but I will assume that each of the 12 arms of the cube have a resistance of R, and let us name them. So let's call it A, B, C, D. Let's call E, F, G. Okay, let me assume a battery is connected between the diagonally opposite corners A to D, which is V, and each arm has a resistance which is equal to R. Now notice one thing, these arms, for example, AF, AH or AB, are symmetrical with respect to the diagonal AD. And likewise, the other three here, ED, DG and DC, are symmetrical with respect to. So we are looking at symmetry with respect to diagonal AD. Now that tells me that the current that is distributed in each such arm must be equal. So let me take these three currents to be equal to I each. So this is I, this is I, this is I. Now likewise, these are the currents which are going out of the point A distributed as I, so that the battery is actually supplying 3I. And these currents will be entering the point D, so therefore these which are entering the point D should also be IIH. Now, when the current I arrives at a point F, because of the fact that the arms FG and FE are symmetrical, so therefore these will have I by 2 each. And likewise, A reaching H will divide into 2, that's also I by 2, and this will also be I by 2. And you can check that the junction rule is automatically satisfied there. And likewise, this will be I by 2, this will also be I by 2. Now notice that we have only used the symmetry of the problem in getting into this situation. So let's look at now this loop A, B, C, D, let's call this E, E, X, V and Y and A. So this is basically this outside loop which contains, so this is the way I'm doing. So look at what do I get out of this. So I get minus IR, minus I by 2R, another IR. So therefore total is minus 5 by 2 IR and then of course plus V. So therefore what I get is 5 by 2 IR is equal to V, which tells me current I is given by 2 by 5 V divided by R, and if I give some numbers, for example, if R is equal to 1 ohm and V is equal to, let's say, 10 volts, then the current I will turn out to be 4 amperes. The current that is supplied by the battery is 3I, which is simply 6 V divided by 5. Now, supposing my question was, what is the equivalent resistance between the points A and B? Now, this can be easily answered by observing that my battery is supplying 3I amount of current. So, current from the battery is 3I. Now, supposing R equivalent is the equivalent resistance of the circuit between the points A and B, then by definition it follows that V divided by R equivalent must be equal to 3I, and which is equal to 3 into 2 by 5 V by R, because that was the value of I. So, this is equal to 6 by 5 V by R. So, you can immediately see that the equivalent resistance between the points A and B, which are on the diagonally opposite corners, is 5 by 6 R, and if each R is 1 ohm, then of course this is just 5 by 6 ohms. Now, this is an example where if you had a priori assumed that there are 12 different currents in 12 different conductors, you would have a mess. But because we were able to observe asymmetry, we were able to do this problem without much of an effort. What we will do next time is to take up some problems which are complicated and there are no obvious symmetries in the problem, and also talk to you about a few applications of what we have learned under the current discharge.